Welcome to Chapter 7, Part 2, where we're going to be looking at the inverse. Remember, inverse means opposite. So we're going to be looking at undoing an exponential function. The opposite of an exponential function, we're going to find out that that function is called a logarithm. We're going to look at some special cases and some properties of logarithms. So let's start out by looking at an inverse. So remember, we said e is a number. E is an irrational number similar to pi. So if I wanted to graph the function f of x equals e to the x, we're going to start by saying values of -1, 0, 1, 2. E to the -1 is 1 over e, which is a little bit more than 1/3. It's about 1/3. You can check that in your calculator. 1 divided by e, remember e is a button on your calculator. Then, so we're going to say this is approximately 1/3. We're just sketching this. It doesn't have to be perfect. And then we have e to the 0. E to the 0, just like any number to the 0, is approximately 1. E to the 1 is approximately 2.7. So just under 3. And then e squared, I'm going to say that's approximately 3 squared, which is 9. So e squared is just less than 9. Again, you can find the exact value in your calculator. For the purpose of sketching this graph, I don't have to be perfect. And then we know that it is asymptotic to the x-axis. Okay, so we're going to say this is just less than 9. To find the inverse is the opposite, and the opposite means I'm switching points, right? So I had the point -1 comma 1/3. My inverse point will be 1/3 comma -1. I had the point 0, 1. My inverse point is 1, 0. I had the point 1 comma 2.7. The inverse has the point 2.7 comma 1. And then 2, 9 becomes 9, 2. So we can see that now our graph is asymptotic not to the x-axis, but to the y-axis. It's never going to touch that y-axis because it's the reflection of a line that never touched the x-axis. What if I wanted to try calculating this algebraically? So if I wanted to calculate the inverse algebraically, remember we have f of x equals e to the x. We need to rename that. So y equals e to the x. And then to change it into the inverse function, we switch x and y. X equals e to the y. And now I want to solve for y. Well, we don't have a way to solve for an exponent, to isolate an exponent by itself, right? If y was a number, I could take a root, but I'm not trying to solve for e. Remember, e is a number. It's approximately 2.7. Okay, I'm not trying to isolate x. We have no way to isolate y. So we come up with this way to isolate y. Y equals something, right? And what we really want to know is y equals the power e to what power is x? That's the question that we want to ask. And so we use this new notation called a logarithm, L-O-G, to represent logarithm. So logarithm base e of x. So this says e to what power is x? And that's what a logarithm is. We had no way of isolating the exponent before, so we have now a new function that you may not have seen before. Okay, so let's take a look at logarithms. we saw in our last example, a logarithm asked the question, to what power? So if I have log base 2 of 8, notice that 2 is small. It's a subscript. Like an exponent is a superscript, exponent is above our normal line of text. Subscript is below the normal line of text. So we have a log base 2 of 8. And the way that we can answer that question, we can find the value, is saying 2 to what power is 8? Okay, and since we can go back and forth between this idea of to what power represents a logarithm, but raising something to a power represents an exponential function, so now we have a way of converting back and forth between these two forms. I can say a to the x is y. This is exponential form, right? X is in the exponent, so this is exponential. Or I can say now, if I wanted to solve for x, I could say x equals log base a of y. This, x is not an exponent, is logarithm form. A couple things to notice. Remember this variable here, a, was called our base. In a logarithm form, a is still called a base. So no matter what form we're in, exponential or logarithm form, the base is the same. So we can see this with numbers. 2 cubed, or 2 to the third power, is 8. So I can also say that log base 2 of 8 is 3. Base 2 raised to the third power, base 2 of 8 is 3. Okay, and there's a little box that just explains that again. So a logarithm has a base, usually denoted with a b, okay, base b, of a positive number x satisfies the following definition. If b is positive and not equal to 1, so the same rules that we had for exponential functions, then log base b of x is y. If and only if, that means every single time this is true, b to the y power equals x. And that's how we can see that a logarithm is the inverse, the opposite of an exponential function. Okay, so let's try converting some of these. We're given them in exponential form. I can tell that it's exponential form because I have something raised to a power. Now, even though this is not an equation with variables, right, it's still exponential form. It's not an exponential function, but it's an exponential form. Okay, so the first question we need to ask in order to turn these into logarithmic form or logarithm form is, what is the base? So step 1, what is the base? The base is the part that was raised to the exponent, like the base of the table is the part that holds it up. So the base here is 10. Base is 10. So that means when I write my logarithm, it will have a base of 10. Okay, and then the 10 was with the 2. That means the 10 is no longer going to be with the 2. It's on the other side of the equal sign. And that means the 100 is next to the 10. There's a little trick that we can use. And the trick is, if you circle the base, let's try that again, circle the base, and then go around the equal sign away from the exponent. So there's the exponent. I'm going to go around the equal sign. Log base 10 of 100 equals 2. Okay, the 10 used to be with the 2, it's not with the 2 anymore. We could do the same thing going backwards. I identify the base, and then I go around the equal sign. That means 10 raised to the second power equals 100. And we could keep going back and forth. 10, not pointing to the exponent, going around the equal sign, then finally reaching the exponent. So it's in exponential form. Then to put it back into logarithm form, I would say log base 10. I circled the 100, equals 2. Okay, so we can switch back and forth and back and forth. And the first step is always identify the base. So let's look at part B. In part B, again, we want to identify the base. Our base here, the part that's holding up the exponent, is a 3. It's in exponent form, so I'm going to change it into log form. Log base 3 of what? Well, 3 was with the 4, so we're going to go away from the 4 and around the equal sign. Log base 3 of 81 equals 4. Okay, so we have the log form of this second part, the log form of the first part. We actually wrote it twice, but they're the exact same equation there. Okay, I have one for you to try here. So go ahead and try these 3 examples of practicing putting them into logarithm form from exponent form. And then there's a multiple choice here. And for this one, you have to remember what question a logarithm asks, because there's not an equal sign. So I can't change this to give me an equation. Okay. Okay, so for A, B, and C, the first step is to identify the base, then rewrite it, log base that of the one that was on the other side of the equal sign equals the exponent. Okay, let's look at the multiple choice together. What is the value of log base 8 of 32? So this asks us the question, logarithm, remember, means to what power? So I say 8 to what power is 32? So then I say, okay, is 8 a power, or is 32 a power of 8? Well, we have 8 to the first is 8. 8 squared is 64. So it's not a power of 8. So what do these have in common? Well, hopefully you can recognize by now that 8 is a perfect power of 2, and 32 is also a perfect power of 2. Okay, so there's a little trick here. I can say 8 is 2 to the third power, and 32 is 2 to the fifth power. So 2 cubed to what power equals 2 to the fifth? Well, if I do 2 cubed to the fifth power, that would be 2 to the 15. But I don't want 2 to the 15, I want 2 to the fifth. So I have to divide it by 3. 3 times 5/3 is what gives me an exponent of 5. So the answer here is B. Okay, so the trick here was to convert everything to a base 2, because 32 is not a power of 8. However, they are both perfect powers of 2. And then being familiar with those rules of exponents, which we're going to continue to need. So if you're still a little iffy on the rules of exponents, please make sure to reach out and set up office hours so that we can work on those together. Okay, next we're going to look at special types of logs. Now we've actually already seen both of these, but I'm going to talk about how they're special. So when we have a base 10, so we would write that log base 10 of, I'll say x. Okay, this is called a common log. And the reason this is a common log is because when we count our numbers, we're always using base 10. What does that mean? That means we have 10 digits to work with. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then we start over and we use those digits to build bigger numbers. So base 2 means I only have 2 numbers, 0 and 1, and I build all of the numbers out of those 2 digits. So base 10, we have 10 digits to work from. So since that's our common base, we don't have to write the 10. If I see something that just says log of x and there's no number here, this is an invisible 10. Very similar to our square root. We know that that's a square root of, I'll put x, because that's our most commonly used radical, is the square root. So then we just say, okay, we don't have to write the 2 every time. So the common log, if there's no base written down, it's 10. We see this commonly used, especially here in California, with earthquakes. When we have an earthquake, the earthquakes are rated on a logarithmic scale. So if I said there was a magnitude 3 earthquake and I compare that to a magnitude 4 earthquake, the difference is 1 order of magnitude, meaning the magnitude 4 earthquake is 10 times stronger, 10 times more force. That's 10 times as destructive as a magnitude 3 earthquake. So you might hear like a 3.2 is a pretty small earthquake, but a 3.7 is pretty big in some places. And the reason that the numbers that are so close together have such a big difference is because they're on a logarithmic scale. Okay, so it's an order of magnitude, meaning if in the common base, that means it's 10 times bigger. Okay, the natural base, and this is why we've been kind of working up to using this variable e. The natural base is e, and we said that's about 2.7. And the reason we have this is because in nature, if you look at plants and the ratio of even measurements within your face, measurements of trees and the way that their leaves form, this number e comes up a lot. Very similar to pi. Pi is used a lot of times when you're using circles or distances that involve radii. Pi comes up a lot. So e is what comes up a lot when we are using exponential and logarithmic functions. And so if we have a log base e of x, we have a shorthand. Now we can't just drop the e because then we would say it's the same as if we had a base 10. And those numbers are very, very different. So log of x versus log base e of x, very different values. So we can't just drop the e. So instead we have this new notation. It's ln of x. Okay, so in Latin, I believe it is, a natural log, you would read it logarithmic natural. And so ln stands for natural log. Even though it's ln, we do not read that as log natural. Okay, it's the natural log of x. So you will still read this, the natural log of x, or you can say log base e of x. Okay, those are the acceptable ways to read ln of x, the natural log of x or log base e of x. Okay, now those are the two logs that your calculator can compute. Okay, now in class, I'm going to show you where those buttons are if I haven't already. So if you need to compute something that's a logarithm, if you need to estimate it, you would use either a common log or a natural log. Okay, so let's look at some of these properties. The properties are essentially the opposite of what we did with exponents, because a logarithm is an inverse of the exponential function. And so all of our properties of logarithms are going to be just the opposite of the properties that we used for exponents. So if I have log base b of m equals x, the base is b, right? So I can say b raised to the x power equals m. If I have log base b of n equals y, base b to the y equals m. Okay, so that's just our definition of logarithm, gives us our first property. The next one, if we then multiply m times n, that's b to the x times b to the y, then we know that b raised to the x plus y equals m times n. That shows us, okay, that shows us that x plus y equals log base b of mn. So we said base b of mn, m times n, equals x plus y. So if we add two logarithms together, that's the same as multiplying their arguments. Notice the base did not change, okay? The base did not change. So that's where these properties come from. we can say log base b of 3 plus log base b of 5 equals, they have the same base, so we can write them as log base b of 3 times 5. So it changes from addition to multiplication, just like if I am multiplying two exponents, I add. If I'm multiplying two exponential functions, I add their exponents. Equals log base b of 15. Okay, that means that if I'm subtracting, if I had log base b of 3 minus log base b of 5, how did I get subtraction of exponents? To subtract my exponents, I use division. So to subtract my logarithms, I'm going to divide their arguments. Log base b of 3 divided by 5. The negative one always goes on the bottom. Okay? And then lastly, what we can do is we can say exponents are repeated multiplication. So repeated addition should manifest itself as an exponent. So if I have log base b of m, I'm using numbers, of 3 to the 5th, this would be the same as log base b of 3 times 3 times 3 times 3 times 3, which would turn into log base b of 3 plus itself 5 times. So then we can say times 5, which is 5 times log base b of 3. Notice the argument here, 3 times 5 are being multiplied inside of the logarithm. This time the 5 is multiplied after I calculate the logarithm. Not in the argument, not inside of the logarithm, but I calculate the log first and then I multiply it by 5. Okay, so if I add two logarithms, I multiply their arguments. If I subtract two logarithms, I'm dividing their arguments. And if I'm multiplying a logarithm times a coefficient, that coefficient can be manifested as an exponent. Let's go ahead and apply these. The first one we want to write as a single logarithm. So what that means is I want to condense this. I want to write it as small as possible. So the first thing I check is that the base matches. Just like for radicals, we had to check if the index matched. This one is a base 4. This is subtraction, so I know it's going to turn into division. So it's log base 4 of 32 was the positive one, minus 2 is the negative one, so it goes in the denominator. So this becomes log base 4 of 16. We're going to leave it like that because it says to write it as a logarithm. I'm going to challenge you now. What does log base 4 of 16 equal? Remember the question that a logarithm asks. A logarithm asks, to what power? So 4 to what power is 16? We would say 4 to the second power, or 4 squared is 16. So this has a value of 2. Now, the question does not ask us to evaluate it, so we wouldn't give 2 as our answer to this question. But I could have asked you to evaluate it because we have enough information to do that now. Okay, so using those rules, we can simplify it until I have only one logarithm. The opposite of that is to expand it. So now I'm going to say my base is 9. All of my logarithms should be base 9 from here on out in this problem. This was division. Division, I'm going to rewrite it as subtraction. So I have log base 9 of x to the 4th minus log base 9 of 729. Now 729 is not in a fraction anymore because I am subtracting the logarithms. Okay, that's not completely expanded. Our goal is to have only prime arguments. So that means not x to the 4th. I want that 4 to come out as a coefficient. That was our third property. So this becomes 4 times log base 9 of x. Now that first term I can't simplify anymore. However, our second term, 729, is not prime. So I'm going to ask myself, what numbers factor from 729? And we can say, okay, well, 729, it looks like a multiple of 9. Let's try it. 9 doesn't go into 7. 9 does go into 72. 8 times 9 is 72. So that's 81. And 81 is 9 times 9. And all of those 9s can factor out into 3s. So this is actually log base 9 of 3 raised to the 6th power. So just like I did before, I'm going to bring that 6 out of the argument. So we have 4 times log base 9 of x minus 6 times log base 9 of 3. That will be our expanded form. I can't factor 3 any more than I already have. And that is how I know this is completely expanded. Okay, now I have a couple for you to try. Go ahead and try these ones. The first one is condensing, so writing it as a single logarithm. The second one is expanding, so writing it out where our arguments are prime. All right, for the first one, both of our terms have a base of 4, and they're both in logarithmic form. So if they are being added together, then we multiply the arguments. 5x times 3x gives me 15x squared. For the second one, we are expanding. So I said 9 times x to the 5th. The word times tells me I can change that into addition. So I have 9 is my first argument, and x to the 5th is the second argument. And then 9 is 3 squared. It's not prime, so 9 is 3 squared. So I can take that 2 from the exponent and make it a coefficient. And then x to the 5th, I can take the exponent of 5 and make that a coefficient as well, ending up with 2 times log base 3 of 3 plus 5 times log base 3 of x. Now, if you noticed, you might have noticed log base 3 of 3, 3 to what power is 3? It's just 1, right? 3 to the first power is 3. So I could also write an equivalent form of this that's 5 log base 3 of x just plus 2, because log base 3 of 3 equals 1. Okay, I would expect you to have the first form. I don't expect you to be able to see the second form quite yet. Okay. The last thing for this lesson is, how do I use my calculator if the base is not e or 10, right? Because we said those are the ones that are on the calculator. We have the common log. Common means base 10, and natural means base e, right? And the trick here is to drop the base to the basement. The base goes down into the denominator. So let's look at, we saw earlier, log base 4 of 16. If I want to calculate this on my calculator, what I'm going to do is take the 4 and drop it down into the denominator. It becomes log of 16 divided by log of 4. Now I didn't have to choose a common log. I could have chosen the natural log. This is also the same. They're all equal to the natural log of 16 divided by the natural log of 4. It's just a habit of mine. I don't usually put parentheses for my common logs, but it's a good habit to do that. So I went back and I added the parentheses for my common log. Okay, now I could have used common log, I could have used natural log, I could have used a completely different log. Maybe I instead want to do log base 2 of 16 divided by log base 2 of 4. These are still equal. Absolutely, you can do that. Okay, there are some really cool tricks that you can do with a change of base formula to simplify complex logarithms. Okay, but right now, all I want you to focus on is being able to take any logarithm and be able to type it into your calculator. So that's why I'm showing you this change of base formula, so that if you have a logarithm that you need to evaluate or to round and estimate, you know how to do that with your calculator. Okay. For homework or for, I guess, classwork, hopefully, you'll have these 8 problems to do. It's just a couple examples of each type of problem that we saw with logarithms. So combining, condensing, expanding, rewriting it into logarithmic form from exponential form, and then a couple of evaluating. So being able to ask that question, to what power? Okay. Your homework is the Math Excel, 7.2 Math Excel. If you have time in class, you're more than welcome to get started on that. But if you have any questions, make sure to ask them ahead of time or send me an email, and then we'll have a chance to answer questions at the beginning of next class as well.